So, Demis, it's really a huge pleasure to have you here at the Collège de France. And so I want to say a few words about Demis. He will actually talk about his entry into the world of artificial intelligence himself, but I thought it would be useful that I do give you a little bit of a background. So Demis Hassabis is the CEO of DeepMind. I'm sure you all know. He was raised in London. His father, I think, is Cypriot, and his mother, Chinese. And I think we can safely say that Demis is somewhat of a child prodigy. He became a champion chess player at the age of 13. He'd already played most of the adult chess masters. He was fascinated by games that use logic and strategy, and so having played chess for quite some time, at the age of 13 also, he decided to turn his talents to a larger area. He actually got a place at Cambridge University at the age of 16, but he was too young to start, so he decided to focus on other things in the meantime. And so by the age of 17, he joined the computer games company Bullfrog Productions, where he worked as a designer on the game Syndicate, that some of you might remember. And he was the lead programmer for the highly influential Theme Park. So this was a bestseller and won the industry's Golden Joystick Award. And this opened up to numerous management simulation games that I'm sure some of us here know. So after graduating from Cambridge with a first-class degree in computer science in 1997, and of course, in the meantime, he led the chess team successfully for 3 years during that whole time. He went on to start his own company, Elixir, where he developed Republic, the revolution. He also discovered the joys and tribulations of running one's own company at the ripe old age of 23, I guess, yes. So very interesting. You can listen to him on the radio talking about what it's like to have your own company at the age of 23. So during this whole time, he was playing and winning international game championships. And in the early 2000s, he was the world champion of the decamentathlon and the world team champion in diplomacy, and also a successful player in the World Series of Poker. And so having proven himself in world game competitions, he then decided to study the human brain in order to gain further insight into the possibilities that artificial intelligence might present. So after a decade of leading successful technology startups, he decided to go into academia and to complete a PhD in cognitive neuroscience at University College London, followed by a postdoc or postdoctoral work at the MIT and at Harvard University in the USA. So this period of academia was equally successful, with numerous important publications in top journals, including Nature and Science. And during his PhD at University College, where he was a Wellcome Fellow, his work was on the autobiographical memory and amnesia, and his work established for the first time that injury to the hippocampus, part of the brain that causes amnesia, also impairs a person's ability to imagine other situations. Demis demonstrated the neurological connection between the functions of imagination and episodic memory, and both require the ability to construct a scene mentally. His achievement was cited as one of the top 10 scientific breakthroughs of the year by Science. In 2011, Demis decided, after his postdoctoral work, together with some colleagues, to found the artificial intelligence company DeepMind Technologies. They focused on creating learning algorithms to master games in the beginning. And by 2013, they'd created an algorithm called DeepQ Network, DQN, that could play computer games at a superhuman level. And I'm sure he'll be telling us a bit more about this. But this allowed, it was the world's best player of Space Invaders within 30 minutes of its introduction to the game, which I find very amazing. So anyway, the successes of DeepMind are multiple, and I'm sure you'll be hearing more. The chess game against Kasparov, the AlphaGo machine that beat the champions of the ancient Chinese game Go. And so the company's progress in machine learning has combined the processes of deep learning and reinforcement learning to create the new field of deep reinforcement learning. And so one can easily see the promise that this holds for almost every field of scientific study, from medicine to astrophysics, and also the fears and concerns that such powerful AI can represent. And Demis, I'm sure he'll tell you, but I've heard him talk about it, is deeply committed to keeping AI safe and for the establishment of good ethical guidelines for its use. So Demis believes that artificial intelligence can help solve humanity's grand challenges: poverty, environment, health. This year, Nature Medicine published a study of DeepMind's first medical product, a new technology for analyzing optical coherence tomography scans, OCT. This is used to detect retinal disorders, including macular degeneration and diabetes-related blindness. DeepMind AI approaches can actually analyze OCT scans and make diagnoses with 94% accuracy, demonstrably better than human experts. So Science magazine has named AlphaGo one of the top 10 scientific breakthroughs of 2016. Time magazine has listed Demis as one of the world's 100 most influential people in 2017. And in 2018, Demis was on the New Year's Honors List and received the CBE, the Commander of the Order of the British Empire. And in 2018, in May, he was elected a Fellow of the Royal Society, the world's oldest, or almost oldest, scientific association. I actually think the college is older, but we can debate on that. So Demis maintains his academic links and activities, publishing high-profile research papers as well as reviews. I recommend a recent review published in Neuron on neuroscience-inspired artificial intelligence, where he discusses, together with animal psychologists, how the exchange of ideas between AI and neuroscience can create a virtuous circle, advancing the objectives of both fields. This requires collaboration and a common language. Distilling intelligence into an algorithmic construct and co-party to the human brain may yield insights into some of the most deep, enduring mysteries of the mind, including the nature of creativity, dreams, and maybe one day even consciousness. I'm almost done. So since Google acquired DeepMind in 2014, this has been the subject of some debate and agitation in the academic community, as many students and their teachers are leaving academia and creating a potential gap in teaching and training, the lure of joining companies such as Google. So I'm convinced that Demis, given his unique position and his very acute intelligence, will be able to answer these fears and find imaginative ways of nurturing academic training and research that will be essential for this growing field of artificial intelligence. So to end, it's our great pleasure to welcome you here, Demis, in this house of learning, to hear about your past and current research and also about your hopes for the future. Thank you very much.
Thank you, Edith, for that very generous introduction. So it's a great pleasure and privilege and honor to be here giving this talk at the Collège. I'm going to, unfortunately, give this talk in English because I don't want to subject you to my terrible French. But I hope at some point, maybe when I come back here in a few years' time, I'll have an AI with me that will live translate in French in my voice. So maybe that will be next time. So I'm going to talk today about artificial intelligence and I believe the big and profound impact it's going to have on the future. So as all of you know, AI is basically the science of making machines smart. And for me, as Edith mentioned, the journey towards AI for me started with games. And games has been a huge theme running all the way through my life, and are still important to us today as part of our research program at DeepMind. So I started playing chess when I was 4 years old, and started taking it very seriously, captained all the England junior teams, chess teams, as I was growing up. And at the time, I was going to try and become a world champion at chess. That was my dream when I was very young. And of course, if you're trying to get better at chess, what you're thinking about, you're studying books, you're studying grandmaster games, and you're trying to improve your own thought processes. You're trying to improve the decisions that you make. And for an introspective kid, and I was very introspective when I was a child, you start actually thinking about thinking itself. So, of course, I was trying to improve myself at chess, but I started wondering about how was it that my brain was coming up with these ideas, these plans, these moves, and what was the process behind that? And it got me very early on fascinated about the mind and intelligence. So later on, when I was about 8, 9 years old, I actually used my winnings from chess tournaments to buy my first computer. And my first computer is this computer here. It's called a ZX Spectrum, very popular in the UK in the mid-'80s. And that's when I got introduced to programming. I bought some programming books and started programming small games and also adjusting existing games that you could buy. And when I very quickly kind of fell in love with computers and programming and sort of realized that this was a kind of magical machine. Of course, all machines are very useful. And we as humans, we're machine building or tool building monkeys, basically. But there's something special about the computer, I think, as a general purpose machine. Most machines enhance our physical capabilities. So, you know, cars allow us to move faster than we can run. Planes allow us to fly. But I see the computer as an extension of our minds. And it allows us to do more than we can do with just our human brains. And this really brought home to me when I started writing AI programs and also using computers for scientific calculations. And I still find this amusing now, that you can set your computer off on a problem overnight, you can go to sleep, and then the next day you wake up and the machine has solved the problem for you. And I still find that somehow quite magical. So my love of computers and games came together very naturally in the form of writing commercial video games. And I guess the most famous game I wrote was a game called Theme Park in the mid-'90s when I was 17. And this game, Theme Park, in fact, all the games that I wrote in my games career are basically based on AI. So in Theme Park, you can see a screenshot of it here on the right. The idea of the game was that you built your own Disney World. So you started with a blank field and some money, and then you designed the theme park that you wanted to, and the layout of that theme park. And then once you were satisfied with your design, you opened your theme park up, and thousands of little people paid money to enter your theme park. And then they would decide, based on their AI, if your theme park was well designed, if they were having fun. And then the more fun they had, the more you could charge them for the burgers and the Cokes and the balloons in the shops. So there's a kind of economic model underlying that. So in a way, the AI system that was powering the little citizens that came into your theme park was judging the quality of the design of your theme park. And so this was then allowed a feedback loop, so that got you more money so you could build more impressive rides and make your theme park even better. Now, at the time, in the mid-'90s, this was one of the very first types of games called management simulations. There's another game called SimCity that's equally famous around the same time. And these two games were the first of its type. And they were really different and people really liked playing these games. So Theme Park sold nearly 4 million copies around the world. And people loved playing these games because they adapted to the individual. So depending on how you played the game, the AI system would adapt to what you were doing, and you would have a unique experience. So your game would not be similar to anyone else's game. Everybody's game who played this would be different, a different experience. So when I wrote this game, I was already quite interested in artificial intelligence. But this, for me, cemented seeing the reaction to the AI in this game, which was relatively simple at the time, but still sophisticated for games in the mid-'90s. It kind of brought home to me how powerful AI could be as, obviously in this case, entertainment, but also as an incredible tool, powerful tool for us to use. So I decided around then that I was going to dedicate my whole life and career to trying to progress the forefront of AI. So I studied computer science at Cambridge as my undergraduate, and most of my training as I grew up was in maths and computer science. But then later, as Edith mentioned, after I sold my first games company, I went back to university, to UCL, University College London, to study neuroscience. And the reason I did that was I felt we knew about logic systems, finite state machines in computer science, and rules and heuristics, all of these kinds of systems that old-fashioned AI made use of, search trees, all of these kinds of techniques. So I'd learned about that during my undergraduate, but I felt there was something missing. And this idea of learning, this idea of memory and flexibility that actually the brain displays, but computers generally don't. AI systems generally don't. So I wanted to go back to studying the mind and the brain in a more formal way doing a PhD to see if I could get inspiration from how the brain worked and how the brain achieved some of these capabilities, for inspiration for new types of algorithms or new types of architectures and representations. And for my PhD, I actually focused on trying to understand memory and imagination, two aspects of how the brain works that we do not know how to do with AI systems. And although I was ostensibly trying to learn about the brain, we actually discovered something quite important during my PhD with my colleagues at UCL. And we discovered that this area of the brain called the hippocampus, which is shown here in pink in the center of your brain. It's quite a relatively small part of the brain, but it's very important. And it's been known for probably nearly 100 years now that if you damage the hippocampus, then you get amnesia. So you can't remember the past. And this is what happens in tragic diseases like Alzheimer's that attack the hippocampus. But what we did and discovered, I guess, just over 10 years ago now, was that the hippocampus is also responsible for imagining the future. So we know it was responsible for remembering the past, but I hypothesized that remembering the past is a reconstructive process. This, memory is not like a videotape. We reassemble the past from components and we put it back together. And that's why memory is sometimes very fallible. Sometimes we mistakenly remember things because it's not a videotape recording of what happened. It's a reassembly. And I was thinking if that's how memory works, then perhaps the same mechanisms and the same brain areas are important for imagination, which you can think of as construction. So if you think of memory as reconstruction, so putting back components into a way that seems familiar to you from the past, you can think of imagination as constructing new novel ideas or novel imaginations from old components, but putting them together in a new way. So it seemed to me that construction process had a lot in common with the reconstruction of memory. And it turned out we tested this hypothesis on hippocampal patients, patients who had diseases that attacked just their hippocampus. The rest of the brain was intact. And we tested them on their imagination and both counterfactual, like imagine yourself on a white sandy beach. Can you describe what's around you? And also imagining personal plans into the future. And we found that they were very impoverished at imagining these things. So in a sense, it was a bit like they were stuck in the present. So they couldn't remember the past, and they couldn't imagine themselves in the future. But they were, if you were to talk to them for 5 or 10 minutes, and you didn't know what was wrong with them, you would think they were completely normal, because they can process the present completely fine. It's just looking back into the past or mental time traveling to the future that they're not able to do. So these discoveries and a whole host of other things that I learned during my PhD became important inspirations for thinking about how we were going to tackle the challenge of building artificial intelligence, general artificial intelligence. And then around 2010, all these different experiences kind of came together for me in terms of starting DeepMind. I felt at that point, 2009, 2010, that we had enough ingredients, enough ideas, enough components to begin thinking about bringing them together to make fast progress towards solving intelligence. So what is DeepMind? Well, we started it in London in 2010, and the way we envisaged it and the way we run it still today is it's like an Apollo program effort for AI. And what I mean by that is that our dream was to collect together the best research scientists in the world in all sorts of disciplines that could be important for AI. So neuroscience, mathematics, physics, and of course machine learning, and putting them together all into one multidisciplinary team. And also give them the resources like the best engineers in the world and lots of compute power, and see how fast we could therefore progress with all of those resources pulling in the same direction with the same approach. Another thesis behind DeepMind was to a new way to organize science. So although we're a research organization, we're organized quite differently to an academic institute, even though the majority of the people at DeepMind are from academic backgrounds. And the easiest way I can describe this, and I can answer more questions about this in the Q&A at the end if people are interested, is DeepMind is like a hybrid culture between the best from academia, so blue sky thinking, ambitious thinking, interdisciplinary work, and the best from startups, like Silicon Valley startups. So their pace, their focus, and the energy that the best startups have. And we wanted to combine those two cultures together. And usually they're quite distinct and quite separate, and some people think they're not compatible, but I saw no reason why we couldn't take the best of both of these worlds, and therefore come up with a new kind of research culture that would be more effective. And I think that's what we've done so far, at least, with DeepMind. So as I said, it was founded in 2010 in London. In 2014, we decided to join forces with Google. And the reason we did that is we wanted to turbocharge our mission towards solving AI. And the main thing that that was useful from Google was the amount of compute power they had in the cloud that allowed us to do far more experiments at much bigger scale than we were able to do, even as a well-funded startup. So as I said, we joined Google to turbocharge our mission. So what is our mission? Well, the way we articulate it is as a two-step process. Step 1, solve intelligence. Step 2, use it to solve everything else. So, you know, this might sound to you, I mean, it sounds pretty simple to say. And of course, it potentially sounds a little bit fanciful or maybe far-fetched. But I hope that by the end of this lecture, you'll feel that this is at least plausible, that step 2 naturally follows on from step 1 if we solve intelligence in a very fundamental and general way. So more pragmatically, how are we going to achieve this mission? Well, what we're trying to do at DeepMind is to try and build the world's first general-purpose learning system. And I'm going to unpack those words in a second, the idea of generality, one system able to do many things, and the idea that the system learns the solutions to problems rather than being hand-programmed. So that really is the history of AI, actually, is there are two really big different approaches to trying to build artificial intelligence. And one of the reasons that AI now is so popular and such a big sort of buzzword, which it wasn't the case, say, back in 2010 when we started DeepMind, almost nobody was talking about AIs, which is hard to remember given how sort of featured it is now in the press and everywhere. And the reason is because of the right-hand side and the success of learning systems. But most traditional AI was done, and obviously AI is a field that is now 60, 70 years old. And most of the work in that time was done on the left-hand side on what's called expert systems, or sometimes it's called good old-fashioned AI, GoFi AI. And these expert systems, their characteristics are they rely on hand-coded knowledge, specialized knowledge that is hand-programmed into the system. So if you think about it, what happens is that the programmers, the AI programmers, think about the solutions themselves to a problem, say chess, and maybe they talk to domain experts to extract what those domain experts know and encapsulate them in rules or heuristics. And then they try and express those solutions as code. And then those programs, these expert systems, maybe they have some decision-making capability, perhaps they're search trees, these kinds of systems, and they rely on these hand-coded knowledge to come to their decision. But what that means is they can't deal with the unexpected. So if anything happens out in the real world when they're deployed that the programmers didn't think about beforehand, there's no way for that system to gracefully deal with the new unexpected situation. And of course, we know that especially when systems interact with humans, then all sorts of unpredictable things can happen, especially in messy real-world domains. So there's no way, really, for most tasks that you can enumerate beforehand all the possibilities that are going to happen. It's just too complicated. So that means these systems are kind of inherently limited. The other problem is that, of course, you're limited to the things, to solutions that we know ourselves already as mathematicians or computer scientists or scientists to solve ourselves. So we have to know the solution already in order for us to program the AI system with that solution. So what about all of the problems we would like to solve that we don't know yet the solution for? There's no way, of course, of writing an AI system in this way that will help us solve those unknown problems. So that's expert systems, and they're largely inspired by logic. That's where the inspiration for these systems came from. On the other hand, if we look at the right-hand side now and learning systems, the kind of key characteristics of learning systems is they learn solutions from first principles. These architectures, things like neural networks, you just present them with lots of data or lots of experience, and then they decide for themselves, they learn for themselves what are the right insights and the structures in that data in order for them to make the right decisions. And the cool things about these learning systems is that they can generalize to new tasks, and they can potentially solve things that we don't know how to. That's the real promise and potential of these learning systems. And I think it's what makes them very exciting, especially when you think about applying them to scientific problems. And these learning systems, the inspiration for things like neural networks has come from neuroscience. And I put this other word here, validated by neuroscience, which is also important. I think neuroscience provides two things for the field of AI. One is, of course, inspiration for new algorithms. But the other thing is that if you already have an idea for an algorithm, and you think it's a good idea mathematically, and you try and implement it, and you want to implement it at scale, how do you know that it's a good idea? Of course, you can try it, but what happens if it doesn't work the first time? And almost nothing does in machine learning work out of the box. It's usually a very hard slog on engineering before these things work. Well, if you can look at the brain and see that the brain implements something akin to the algorithm that you're trying to implement, then you can have some confidence, actually, that this solution is worth persevering with and worth pushing harder. And eventually, if you implement it in the right way, it should scale. And when you're talking about a very large research project with potentially hundreds of researchers and engineers on it, so there's a lot of resource, and you don't want to waste their time, then having some guidance, a little bit of like a breadcrumb trail from what neuroscience tells you, can be very, very important and can be the difference between success and failure. So that's why we take neuroscience so seriously at DeepMind, and it makes us quite unique amongst the companies that are trying to work on artificial intelligence. We consider neuroscience as a sort of first-class part of our research, not just a nice to have. So still the most famous example of an expert system probably ever is IBM's Deep Blue machine, which I'm sure you're all familiar with. If you remember from the late 90s, this was probably one of the biggest watershed moments in AI. Deep Blue took on Garry Kasparov, who was then the world chess champion, and won the match in the late 90s, 1997. And I remember watching this match. Of course, you can imagine I was fascinated by this match from two directions. One, it was about chess, and the second, it was about AIs and computers. But funnily enough, I came away from this match actually more impressed by Garry Kasparov's mind than I was with the machine. And that's because here was Garry Kasparov, competing on more or less a level playing field with this brute of a machine. It was a huge supercomputer that Deep Blue, that IBM was using. And Garry was able to compete with the machine on chess. But of course, Garry can do a myriad of other things seamlessly that humans can do. Drive cars, speak many languages, all sorts of things, with the same apparatus that he was using for chess. And yet, if you look at Deep Blue, all Deep Blue could do was play chess. There was nothing else in Deep Blue's program that would be useful for any other task. Even strictly simpler tasks like playing noughts and crosses or tic-tac-toe. I don't know what it would be called in France. But it's a very simple child's game. And nothing in Deep Blue's programming would help to solve and play even a much simpler game like that. And you would just have to reprogram it from scratch, throw away all of the Deep Blue's chess knowledge, and start again with new knowledge. So it seemed to me something very vital was missing from Deep Blue, if you want to think about it as an intelligent system. Right? So it was doing something seemingly intelligent, playing chess to world championship level, but it was very narrow. And the two things that we felt, and I felt, was missing from it was this notion of generality. So one system being able to cope with many tasks, some of which perhaps it's never seen before. And this idea of learning and improving for itself. So actually improving through experience and gaining knowledge for itself. And the flexibility of being able to do that. So generality and flexibility. And Deep Blue and expert systems don't have either of those properties. So how do we think about intelligence then on a technical level at DeepMind? Well, what the kind of framework that we use is called reinforcement learning. And it's quite a simple technique to explain, but it's very powerful, and it's also biologically inspired. So I'm just going to briefly explain what reinforcement learning is with the aid of a simple diagram. So if you see this image on the left, the little character on the left, which we call an agent, that is the AI system. Now imagine the AI system, the agent, is embedded in an environment of some sort. Now, if the environment is the real world, then the agent would be a physical robot. If the environment was a simulated digital environment, like a game, which is what we use at DeepMind mostly, then you can think of the agent as a virtual avatar. And the agent is in this environment, and it's trying to achieve a goal. Now, the agent interacts with the environment in only two ways. Firstly, it gets observations and rewards from the environment. So it gets that through its sensory apparatus. So we mostly use vision at DeepMind, but we are also starting to explore other modalities like audio and also things like touch and potentially others that you could have. But for the moment, we mostly use vision. And the agent's job is twofold. First, the first job of the agent system is to build a model of the environment, as accurate a statistical model as it can, to make predictions about the environment. And so, it's getting this observations about the environment in real time, and it has to update its model about how the environment works based on these observations. And then once it has a model, what can it use it for? Well, it can use the model to try and make predictions about what would happen if it took certain actions, and what would happen to the environment, and especially importantly, would it get any reward? So the agent has to kind of do a search through the possible actions that it has available to it at any one time, and then think about what change would that drive in the environment. And then once it's run out of time to think, it outputs and executes the best action it's found so far that will get it closest towards its goal. And over time, this whole system operates in a circle. That action gets executed, that may drive a change in the environment, that drives a new observation, and then the agent then updates its understanding of the environment and its model of the environment. And as that model gets more accurate, the agent's decisions become better. And eventually, through a process of trial and error, the agent can eventually get towards its goal. Now, this diagram's very simple to sort of show and to explain, but there's actually a lot of very tricky technical complexities underlying reinforcement learning that have to be solved and are yet to be solved. But we know that it's worth persevering with because the brain uses reinforcement learning. Our brains use reinforcement learning as one of our main learning mechanisms. And in the human brain, it's the dopamine system and the dopamine neurons that implement a form of reinforcement learning called TD learning. So this idea then of learning from first principles has really taken off in the last decade and has become very, very powerful at scale. And at DeepMind, we use games as the sort of testing platform for developing our algorithms and testing their capabilities. And we also use robots, and we also use real-world data. But a lot of the majority of our pure research work is done in simulation. And we think that that's the most efficient way to do this kind of research. Because when you deal with physical robots, if any of you in this room work on robotics, you'll know that they're very fiddly, they're very expensive, and they break quite often. So you actually end up spending most of your time working on the hardware rather than thinking about the software and the algorithms themselves. So we wanted to focus on the algorithms. And if you're running simulations, you can run them faster than real time, and you can run millions of experiments in parallel in the cloud. So it's a very powerful way, an efficient way of doing research in AI. And the other nice thing about games is usually they have quite a clear objective, and they may even have a score. So this is quite useful for us to optimize and for a reinforcement learning system to optimize and be able to measure if they're getting incrementally better. So the first big gaming system that we tested this on was the classic 8-bit Atari games from that many of you here will be too young to remember, but from the early 80s. And really, it was the first iconic game console that had lots and lots of very interesting games. So our first big piece of work was testing our AI algorithms on more than 50 different Atari games. And they all look completely different. Different rules, different graphics, different ways of getting points. So every one of these games was entirely different. And we wanted an AI system that could learn to play all of these different games just from the raw pixels, just from the raw pixels on the screen as inputs and nothing else. And the goal for this system was simply to maximize the score. Everything else was learned from scratch. So it didn't know what it was controlling. It didn't know the rules of the game. It didn't know how to get points. All of that it had to learn from scratch. And then we had this additional constraint, which is that we wanted one single system, one single algorithm that was able to play all the different games out of the box. So this is that notion of generality again, a general system that can play all 50 or more than 50 Atari games. So I'm going to show you a video now of, it's my favorite video of the Atari system working called DQN. And this game I'm going to show you is called Breakout, which is, the idea of the game is that you control this bat and ball at the bottom of the screen, which you move left and right, and you're trying to bounce the ball off this brick-colored wall, and brick by brick. And if the ball goes past the bat, you lose a life. So I'm just going to show you how the AI system improves over time. So this is it after 100 games of experience, so not that many games yet. And you can see that the system yet is not very good. It's missing the ball most of the time, but it's starting to get the hang of the idea that it needs to move the bat towards the ball. Now, after 300 games, you can see the system's got very good now. It's pretty much as good as any human can play this game. So it can almost always get the ball back, even when the ball's going very fast, at very vertical angles. And then we let the system just play 200 more games. And then this amazing thing happened that it dug a tunnel around the left-hand side of the wall and then sent the ball around the back of the wall, right? And which is an amazingly efficient strategy, and it's very safe because obviously you can't lose a life when the ball is behind the wall. And it may look obvious now. Now I've shown you that strategy, and of course it's doing it with superhuman precision. But at the time, this is the first case, and we've had many others since then. This is 5, 6 years ago now, of us learning something from our own system. Because the people that were, the amazing researchers that were working on this system did not know that strategy. So they discovered that strategy by watching our own algorithm play the game. And I think this is going to be, maybe that's the first moment of something that's going to become more and more common. So for us, that was our first big research breakthrough, and it led to a front cover article on the front cover of Nature. And we also released the code. So if you're interested in tinkering around with this type of algorithm yourselves, you can download it from the Nature website. And then our next big sort of landmark event, probably the thing we're most famous for now, DeepMind is most well known for, is our program AlphaGo. So we took all of these ideas with DQN, and now we scaled it up, many orders of magnitude. AlphaGo is our program to play the ancient Chinese game of Go. And this is what a Go board looks like. It's played on a 19 by 19 grid, and you take turns placing your pieces on the vertices of the board. And the idea of the game is that you are trying to surround your opponent's stones, or you're trying to wall off empty areas of territory, and I'll show you that in a second. Now, the history of Go is that it's more than 3,000 years old. It's the oldest game humans still play. It's just as popular as ever. There's 40 million active Go players in the world. And the complexity of Go is immense. So just one simple way I can illustrate that is that there are 10 to the power 170 possible board positions in Go, which is far more than there are atoms in the observable universe. So there's about 10 to the 80 atoms in the universe. So what that means is, even if you took all the world's computers and you ran them for 1 million years, you still would not be able to calculate every variation in Go. It's just simply too large. So the aim of the game and the way the game ends is that this is the end position of a game of Go. And once there's no more places for you to place your stones, sensible places to place them down, you count up how much territory, how many squares did your stones wall off versus how many points of territory did your opponent wall off. And then the winner is simply the player with more territory. So in this game, actually, it's very evenly balanced, and white wins by 1 single point. Now, why is Go so hard for computers to play? So I already mentioned Deep Blue conquered chess 20+ years ago now. And after that, Go was really the next big challenge, grand challenge for AI. And it was thought to be the sort of Mount Everest of games AI research. And there's 2 main reasons why Go took another 20 years. And also these sort of traditional expert system methods that I outlined earlier do not work at all for Go, right? And that's what people were trying for until AlphaGo came along, these sort of traditional expert systems. And they were never able to get even as good as beating a professional player, let alone the world champion. So there's 2 reasons for this. One is this enormous search space, which I've just mentioned, in the vast number of possibilities. And second thing, probably the even tougher thing, was that it was thought to be impossible to write what's called an evaluation function. And what an evaluation function is a function that tells the system in this position which side is winning and by how much. And obviously, that's critical for a machine or a human player to decide what move to make. An evaluation function is absolutely critical to that program. Now, in chess and these kinds of expert systems, that evaluation function is hand-programmed. And it's very easy. If you know how to play chess, the first rule that you write down is you count up the value of the pieces on each side. Queen is 9 points, a rook is 5 points, a knight is 3 points. And you count up the number of pieces on both sides. And to first approximation, whoever has the most value pieces is currently winning in that position. And that's quite a good first heuristic. And the modern chess computers, which are extremely strong, have thousands of heuristics like that they try and balance against each other and tells the system, the machine, which side is winning. But in Go, because Go it does not have material, as you saw on the Go board, there's only one type of piece, a stone. So, and it's much more esoteric than chess. It's about patterns. So in fact, Go players consider Go to be an art form, not just a game. So in China and Japan and Korea, where they play Go very seriously, it occupies the same intellectual echelon as chess does in the West, but in fact is even more sort of profound. They think of it as a sort of philosophically and artistically. In fact, Confucius wrote that Go was one of the 4 great arts any true scholar had to master. So it's really thought of as an art form, and actually human players overcome this complexity by relying on their intuition. Whereas chess is much more about calculation, Go is a lot more about using your intuition. And of course, intuition is not something that you'd normally associate with computer programs. Right? Calculation, of course, is something we know computers do well, but not intuition. And we overcame these 2 problems by using neural networks. 2 neural networks, actually, to address both of these issues. So the first neural network we trained was called a policy network here on the left-hand side. And we trained this system on expert player games, human games, professional games. And we trained it to predict what move the professional would make in that position. And it got pretty good at doing this. So you could give it as an input a board position, here that's shown there in blue at the bottom of the screen, and the output in green would be a probability distribution over the likelihood of a professional player playing a particular move. So what this means is, instead of searching all the different possible moves you can play in a position, which is often, on average, more than 200, you can actually focus on, say, the top 3 or the top 5 most probable moves. Secondly, on the right-hand side, we created a second neural network called the value network. And this value network became the fabled evaluation function. But instead of us programming all these different rules and heuristics, we left this neural network to learn for itself what was important and valuable about a Go position. And we did this by having the system play against itself millions of times and seeing the outcome of those games. And often at the beginning of the training, those games would not be very high quality. And it would see what was the end result. And then it would look back at the decisions it made and the positions it was in, and it would adjust its evaluation of those positions. So if it lost a game, it would adjust its evaluation of the positions that led up to that loss to evaluate them as slightly worse next time it was in a position that was similar to that. And over this process of incrementally learning through reinforcement learning and getting these rewards, the only rewards it was getting was 1 point for winning and 0 points for losing a game. You can, over time, learn an evaluation function for Go. So once we built that system, we were ready to challenge the best player in the world. And this we did in 2016, a couple of years ago now. And we played this South Korean grandmaster called Lee Sedol, who is a total legend of the game. He's the greatest player, considered to be the greatest player of the past decade, and he's won 18 world titles, and was still at the top of the game. So we used to call, the kind of analogy for him, he's like the Roger Federer of Go world, right? So legend for over a decade, but still at the top. And we challenged him to a 5-game match in South Korea, in Seoul, and for $1 million. And everyone, including himself, before the match was predicting that he would win 5-0. And the machine would have no chance, because no one had ever seen a Go program that was even capable of beating a weak professional. And here was, probably one of the greatest players of all time. So ostensibly, there was no way that a computer program could have bridged that gap. So this was a huge event, especially in Asia. Over 200 million people watched the match, and the whole of South Korea pretty much came to a standstill during the week of the match. And to everyone's surprise, AlphaGo won the match 4-1. And many of the world's experts, both in AI and in Go, said it was at least a decade before its time. And for those of you in technology and science, know that almost nothing you work on ends up being a decade before you expect it to. It's usually the other way around, right? It's usually a decade after you hope it was going to happen. So this was quite a surprise for us as well. Now, of course, winning the match was great. That's what was our objective. But actually, more important than winning the match was how AlphaGo played and how it won. And I just want to show you, even if you don't play Go, and if you don't play Go, I really recommend it to you, because it's an amazing game, especially if you're a mathematician or physicist. It seems to really appeal to the mathematical mind. But I want to explain to you anyway what AlphaGo did in game 2 that really amazed and shocked the Go world. And it was move 37 of the game, which is quite early on in the game of Go, which can last a couple of hundred moves. Now, AlphaGo here, this is the board position in game 2. AlphaGo is black and Lee Sedol is white. And AlphaGo played this move here for move 37 on the right-hand side, circled in red. And you'll notice that this stone is on the 5th line of the board. And almost all the other stones on this board are either on the 3rd or 4th line. Now, in the openings of Go, 3rd and 4th lines are the lines which are usually disputed and are considered to be the most important places to play and establish your territory. And so for thousands of years, the received wisdom in Go is that playing on the 5th line like this early on in the game is unthinkable. It's just a terrible idea and a terrible move. And yet, AlphaGo here boldly plays this early on move 37 in this position. And the whole Go world could not believe this, and all the live commentators, they literally nearly fell off their chairs when they saw this move, and they thought there must be some kind of bug with AlphaGo for it to play this move. It's kind of incomprehensible. And yet, what happened is that 100 moves later, so more than 100 moves later, these two stones here on the other side of the board that I've marked in red, the fighting over in the bottom left, the struggle that was going on in the bottom left, spilled out into the center of the board and then all the way connecting with this move 37, 100 moves later. And it turned out that that stone there, move 37, was in the perfect place to decide the match, decide that fight and therefore decide the match. So it's almost as if AlphaGo had presciently understood that that stone was going to be in the perfect position later on for an entirely different reason. And that's how it turned out. And that's the nice thing about Go, is it is like an art form, but most art is subjective in terms of its quality, whereas Go is objective art. So, we could all here play a creative move in the sense of we could play a random move in this position, and it would be a novel idea in some ways, and a move maybe that a professional would not make. But the point is what makes it creative and worthwhile is if it affected the game, if it helped win the game. So you can evaluate objectively whether this creative idea was any good or not. And by that measure, move 37 was an amazingly creative idea. And this is what Lisa Doll said after the match. He said, "I thought AlphaGo was merely a machine based on probabilities. But when I saw this move 37, I thought surely AlphaGo is creative." And that really changed his mind about what the game was about, but also the power of AI. I must mention just briefly, I haven't got time to explain this, but Lisa Doll himself was inspired to come up with his own brilliant move in Game 4, which is the game that he won, move 78, this move in the middle here called a wedge move, that also astounded the Go world and will probably go down in Go history. And he confused AlphaGo and made AlphaGo misevaluate the position, and he won that game in a brilliant way. And overall, Lisa Doll was inspired by the match, and in fact, the whole Go world has been inspired by AlphaGo's play. And many of the professional Go players have said to me afterwards that they now feel that they're free. They freed their minds from the shackles of tradition, and they're now able to think unthinkable ideas. So not only are they using some AlphaGo ideas that we released hundreds of games, example games from AlphaGo that are being studied now, but also they were able to be free to think up new ideas for themselves that perhaps over the last 100 years they've been constrained more by tradition. And if you're interested to see more about the technology behind AlphaGo and what happened, I urge you to watch this documentary, award-winning documentary by Greg Coase, this great director, on the whole match, AlphaGo match, that's on Netflix now. So coming full circle then back to where I began this talk, we now have extended AlphaGo to become much more general. And we've created this new system, which is, we're about to publish a big paper on this in the next couple of weeks, and we call this system AlphaZero. And what AlphaZero is, it's generalized in two ways. It generalizes AlphaGo to now not just be able to play Go, but play any two-player game, including chess and shogi. Shogi is Japanese chess, also played professionally. So AlphaZero really is the culmination of all of the dreams I had when I was young about a general games playing machine. So if you think about what I said about Deep Blue and my criticisms or my critique of what Deep Blue was, it couldn't play even a simpler game like Noughts and Crosses. AlphaZero can play any two-player game out of the box within a few hours. And the other key thing about AlphaZero is it learns completely from scratch with no human data. So AlphaGo, if you remember what I just said earlier about the policy network, it needed to see human professional games in order to understand what kinds of moves were likely to be played in certain positions, and that helped with the search. But AlphaZero doesn't need that. AlphaZero can start from totally random play and effectively evolve itself through multiple iterations of improvements of itself, through playing against itself millions of times, get all the way to world championship level at any of these games. So it learns from first principles completely from scratch. And of course, we tested it on my favorite domain of all, which I couldn't resist, which was chess. And we tested it against the current world chess champion engine. It's called Stockfish, which you can think of as a descendant, a very powerful descendant of Deep Blue. Using the same kinds of systems, all these inbuilt rules. Stockfish has over 1,000 rules and heuristics that help it play chess. And of course, it's much, much stronger than any human can play chess already. And yet, and it was thought to be unbeatable, Stockfish. Maybe it was already playing chess at the most optimal level you can play the game. And yet, AlphaZero, we played a 100-game match, and AlphaZero won 28-0. Beat Stockfish 28-0 with 72 draws after just 4 hours of training. So you start it at lunchtime, it's playing randomly, and then at tea time, it's better than the best chess-playing engine of all time. So I just want to sort of leave you that thought. That's the kind of magic, and we still feel that's quite magical at work, even though we're used to this, seeing that progression. And the other cool thing about AlphaZero is not only was it so strong, it seems to have invented a new style of playing chess. And I haven't got time to explain this much, but there are a lot of very cool YouTube videos from strong chess players who've commentated on some of the games we released. And I urge you to go and look at those if you're interested at all in chess, because I think you'll appreciate the style that AlphaZero plays in. It doesn't play like a human, but it doesn't play like a computer engine either. And one of the things it likes doing is it favors mobility, the mobility of its pieces, over material. And that's one of the things that chess engines like, is they like material. They like taking pawns and holding onto pawns and pieces. And that's the kind of engine style of playing. And instead of that, AlphaZero likes sacrificing its pieces for mobility. And I have a hypothesis why this is. And I think one of the reasons why this is because AlphaZero does not need to overcome any inbuilt rules. Right? So if you think about Stockfish, it has a rule in there that says a rook is worth 5 points and a knight is worth 3 points. So if you want to exchange your rook, you sacrifice your rook for a knight, that's -2 points. So in order for Stockfish to make that move, it needs to figure out through masses of calculations that it's going to get those 2 points back in some way later down the line. But AlphaZero doesn't have to do that. It has no conception, preconceived notion of what these pieces are worth. As far as it's concerned, they're just assets that are to be used for its goal of winning the game. So that means in any particular new context, any position it sees, it can just dispassionately evaluate these assets. And in a particular position, it can say, right, my opponent's knight is doing more in this position than my rook is doing, so I'm just going to swap that off. And that's going to be beneficial for this particular position in terms of the context of that position. It doesn't have to overcome this inbuilt rule and justify its own decision that it's going to get the 2 points back later. Now, I've walked you through a lot of interesting and big breakthroughs that have now really advanced the field. And it's a hugely exciting time to be in AI. But of course, I don't want to give the impression that we're anywhere close to human-level general artificial intelligence. I think we are several decades away from anything like that. And there are many, many challenges yet to be overcome. And I'm just going to list a few here that I haven't got time to go into. But unsupervised learning. So this is learning when you don't have any reward. Memory and one-shot learning. Can you learn from a single experience rather than needing millions of experiences that our systems currently need now? Can you use this imagination, like I mentioned in my neuroscience? Can you imagine the future, imagine different plans into the future? We're not able to do that at the moment. Can you learn abstract concepts? That's something, again, our systems are not able to do. Can you transfer your knowledge from one domain to a new domain that you've never seen before? Also very hard. And I haven't shown you anything today. None of our systems are able to do things like language understanding. So we're still at very much a kind of primitive level. So there's many interesting challenges that remain. And I just want to finish by talking on a section about this step 2. what happens when we have general AI? What can we apply it to? Well, of course, I think the possibilities will be almost limitless. If you think about what intelligence, human intelligence, has done already, look at this city around us, this lecture hall. This is what human intelligence has built over thousands of years, is modern civilization, which if you stop and think about it is pretty incredible. But that was intelligence that built that. And so what could we do if we had these amazingly powerful tools to aid us? And we don't have to wait all the way to resolved intelligence to do that. We can use the systems that we already have today, already can be quite powerfully applied to all sorts of useful real-world cases. So we and many other companies are applying these kinds of techniques I've just shown you to healthcare, medical diagnostics. We're doing that with the National Health Service in the UK. Edith mentioned a few of our works on that, doing retina scans, and we're also working on head and neck cancer scans, all sorts of things to help diagnostics. We've also used it for industrial optimization. We now control all the energy usage in Google's data centers, and we've managed to save more than 40% of the energy they use. You could use it in education to personalize education to the individual student, and you can make things like virtual assistants on your phone more intelligent. So there's a myriad of possible applications. These are just examples of some. AI is not just limited to commercial applications. It's been going into the realm, admittedly, just the beginnings of art and design. So here's an example on the top left of an opera house that was designed with AI, helped to design that. On the right-hand side there, I don't think it's a very high-quality painting, but it is the first painting to be auctioned by Sotheby's. It went for $500,000. I don't think I would have paid that for it, but perhaps it is worth that. Made by an AI system that created that painting. And then the bottom right there is an example of an AI-designed engine block, which you can see is much more organic looking than normal and apparently much more efficient than normal components for the engine. But for me, my personal passion is to use this for scientific discovery, use these powerful tools for scientific discovery. And this is already happening wherever there's a lot of data. So exoplanet discovery, controlling the plasma and nuclear fusion reactors, coming up with new chemical compounds, and doing things like scanning for disease in retinas and other brain scans. So all of these systems now are being put to use in all sorts of scientific and medical endeavors. And you can think of three properties or problems that are well suited to AI systems, even that we have today, these kind of AlphaZero-like systems. One, they should be massive combinatorial search space. That should be the nature and structure of the problem. Two, there needs to be a clear objective function or metric to optimize against, like a score or an energy function, all sorts of things. And there either needs to be a lot of data, or you have to have an accurate and efficient simulator of that physical system. Now, these three sort of constraints or properties, if you like, actually turns out a lot of scientific problems, probably many of the problems that you're thinking about or working on now, actually do fit these kinds of properties, this kind of desired properties. So already, we're applying our AI systems to quite a lot of big problems. The main one we're working on is actually protein folding and the problem of determining 3D structure of proteins from the 2D sequence. So I just want to finish by just stepping back and just thinking a little bit about the philosophical level of what working on AI means. Now, I see as the challenge, one of the massive challenges facing society today is information overload and system complexity, both in our personal lives, in things like entertainment, to our professional lives as scientists. And the sorts of systems we would like to master now, let's say, climate or perhaps macroeconomics, they're so complicated, it's very difficult for even teams of the world's best human scientists to understand and find the insights in all the vast amounts of data and complexity that's there. And the buzzword before AI, sort of the last decade, in the early 2000s, was big data. And everyone was going on about, we've got to acquire more data, big data. Actually, the way I saw this is that big data is really the problem. Everybody has tons of data now. Every company, every scientist, every individual consumer has a ton of data. The problem is how do you process that data to find the insights in the structure in that data and discover things hidden in that data? And I believe AI is the answer. And you can think of the kind of AI I've been discussing, this general AI, as a kind of process that converts unstructured information and converts it into useful knowledge, almost like a physical process. And for me, the dream is to use AI as a powerful tool to accelerate scientific and medical breakthroughs. And I just want to end with one slide on ethics and social responsibility. So AI holds, enormous promise for the future and these incredibly exciting times, but we have to build these systems, they're very powerful systems, responsibly and safely, and make sure they're used for the benefit of everyone. Like any technology, AI is, I think, inherently neutral. It depends on how we as humans and society decides that we're going to deploy it that will determine whether it's for good or for ill. And much more research and discussion is needed in big formats and forums like this with the general public to discuss how this technology should be used on the wider scale and the impact of that. And we've co-founded a couple of organizations, one within DeepMind and one with other industrial and academic partners, the Partnership on AI, to begin those discussions. And as a neuroscientist, I just want to quote one of my favorite scientists from the last century, who said, Richard Feynman, who said, "What I cannot create, I do not understand." And I believe that for intelligence, that this kind of neuroscience-inspired AI path towards trying to build AI could be one of the best ways of understanding our own minds. If we try and distill AI into an algorithmic construct, I think we can then compare that to the human mind, and perhaps that'll unveil some of the profound mysteries of our own brains, like the nature of creativity, dreams, and consciousness. Thank you for listening.